Oh, sure. Yeah, that's a great idea. We could always just vote. And that way you guys can go through and choose the particular problems you'd like to see. I think that's a great idea. Should we do that, folks? Let's see how to vote, because the numbers are all wonky. But, I mean, that could still work. Maybe that's the best idea. Or we could do something in the middle where I say, these are the ones I think are most important.
Yeah.
Is that right? All right, that does narrow it down a little bit, doesn't it? Now, why is my... I'm trying to get my camera to work, because there's at least 3 people not here, so I want to record. Weird. Well, I suppose I can just do it. Okay, well, we'll just do it. All right. Also, I have your tests to give back to you after class, so you can get that feedback afterwards. Hey there, Anna. Anna, I was just talking with everybody about how we could do today. Since a lot of you are just now getting the practice final right now, it'd be tough to do, people signing up to do problems per se, because a lot of people just now saw it, so they may not be sure what to sign up for. And then also, the practice test is very long, so we're never going to get through all of it. So we were just talking about me just highlighting which problems in there are the most important. Okay, so let's go for it, folks. I'm going to have a copy. Did everyone get a copy? All right. So let me put through here. I have some more problems up here that you guys don't, but we'll still just focus on the individual problems. So first, here we are. Today is May 3rd, and we're doing our review for the final. Yeah, all of these problems are somehow or another taken from your homework. So you can always go back and look through your homework packets and see solutions for these problems. And then our exam is on Tuesday, and it's a little bit of a different room. I'm sorry, a little bit different time. Isn't it Tuesday at 10:30? Yeah, so you have to be here a little earlier than usual, because the final exam is Tuesday at 10:30, and I think I just sent you all an email via Canvas telling you that. So maybe just write that up at the top, Tuesday at 10:30. That way everybody knows to be here Tuesday at 10:30. Okay, I have a few jokes here for you. I'll just do one, and then I can do one next time. What do you call a boomerang that doesn't come back? What do you call a boomerang that doesn't come back? A stick. Yeah, terrible. I know. Okay. All right. Well then, let's go ahead and we'll start at the beginning. First question, very good one, is 7. So number 7. Now, maybe I don't even need to present this stuff on the board because you're all looking at it. But we're looking at number 7, folks. So in number 7, it says a vehicle purchased for $25,000 depreciates at a constant rate of 9% per year. Determine the approximate value of the vehicle 10 years after purchase. I don't know that we've necessarily done a problem exactly like this before, but this is not a calculus problem. It's just talking about rates. So I'm going to show it to you here. The vehicle purchased for $25,000 depreciates at a constant rate of 9% per year. So let's look at this for a second. First of all, it's depreciating. Yes, losing value at 9%. And so the way we want to think about this is, how much of the value of the car are we keeping? What percent of the car's value stays? How much is it? 91% of the value stays. So the function that we're actually looking at, if we wanted to write a formula, would be y equals 25,000 times 0.91 to the power of x. That would be how you would represent a certain value depreciating over time. you don't focus on the fact that you're losing 9%. You focus on the fact that you're keeping 91%. And a fun way to see this on your calculator is just to go ahead and, everybody, go ahead and type into your calculator 25,000, enter. So 25,000, enter. And then hit multiply by 0.91. And you'll see the value of the car drop from 25,000 down to 22,750. So over the course of that first year, you kept 91% of the value of the vehicle. You lost 9% of the value of the vehicle, but you kept 91%. So now if you hit times 0.91 again, now you have 20,702.5. So again, you lost 9% of the value that year, but you kept 91% of the value. And now you can just start hitting enter, enter, enter. And you can see the value of the car going down over time. Now you're at 18,839 with some change, and 17,143 with some change, and then 15,600 and some change. The main idea here is that when you look at a depreciation problem, you're multiplying by a number less than 1, because that way the value is getting smaller over time. And furthermore, you're not focusing on what you're depreciating, you're focusing on what you're keeping. So you might refer to that as your keep value. All right? So what is this question actually asking us for? Determine the value of the vehicle when? 10 years later. So all you would do is just do y equals 25,000 what? Times 0.91 to the 10th. And that's it. You can type that in your calculator, 25123 times 0.91 to the 10th. And the value of the vehicle 10 years later is 9735.4. Now, what does that look like in a graph? In a graph, we've got the 25,000 times 0.9 going to the x. Well, in a graph, there we go. So there you can see what's happening to the value of your car. You start here, the car is 25,000, and then it starts depreciating and losing value. So how would you feel if you just spent $25,000 on a vehicle? And then even 10 years later, what's your car worth? Yeah, like 9,000. And see, this is why a lot of people don't buy brand new vehicles. Like, do you know who people who, like, they only buy brand new vehicles, but then you know people who never buy brand new vehicles? You lose a lot of the value of the car within the first couple of years. I mean, in fact, when do you lose half the value of the car? Take a look. If you start at 25,000 and then you're down to 12,500, you've lost half the value of the car in nearly 7 years. So on the other hand, you could buy a vehicle that's 6 or 7 years old and spend a lot less money. Anyway, that's what the modeling looks like. Okay. Number 8, you set up almost identically, except now, read it with me, a bank features a savings account that has an annual percentage rate of 3% with interest compounded quarterly. Now the value of this bank account is going up over time. So notice, when the value of something goes down over time, the number that you're multiplying by is less than 1. So if the value of something is going up over time, this number should be bigger than 1. So let's take a look at how to set it up. This is a bank account with an interest rate of 3%, compounded quarterly. So what's our formula for compounded interest? Well, this is compounded quarterly, so we'll use the normal compounding formula, not the continuously compounded, which is PERT, but the other one. So 1 plus r over n to the nt. So what do we have here? She deposits $8,000 into the account. And now notice that since it's compounded quarterly, n is 4, so that's 1 plus 0.3%, so 0.03 over 4 to the nt, so that's 4 times. How many years are we doing it? Oh, well, we'll just put t for now. So what Shannon has in her bank account then is 8,000 times, what's 0.03 divided by 4? Is it Why?
0.0075.
Okay, perfect. So now that's what we have. We have Shannon investing her $8,000, and the number that she's multiplying by over and over and over again is 1.0075. So in the case of the car that's depreciating, the value is less than 1, and so overall the value of the vehicle is going down, and you're looking at the value that you're keeping. Likewise, now here, the value of her money in her account is going to go up, and the 1.0075 is a number bigger than 1, and it represents the value that she gets to keep, which now she's getting extra money every year. So anyway, I just wanted to call your attention to that whatever the number is that you're multiplying by over and over again, if it's less than 1, that represents depreciation, and if it's more than 1, that represents growth. So how do we actually calculate how much money she'll have in 8 years? What do we do? Well, what specifically do we have to do with our formula now? You just plug in 8 for t. So it'd be 8,000 and then 1.0075 to the power of 8 times 4, which is 32. And so you plug that in, and that will give how much money she has in the end. Part B, the question that says, what's the APY? You can cross that out. I don't think we ever did an APY problem, did we? I don't think we did. You can cross out APY.
Yeah.
Oh, you don't even have it. Okay, we're great. So I already deleted that for you. Okay, so that's just 2 good questions that are talking about growth and depreciation. So that's not exactly calculus yet. It's just making sure that we know how to use those. Oh, right. Okay, I did delete that for you. Okay, so we're going to touch on some of these questions quickly. Number 9, how do you evaluate average rate of change from 1 to 3? So they're saying use the graph of f to evaluate the average rate of change of f from 1 to 3. Where am I measuring the 1 to 3 from? Yeah, left to right on the x-axis. So we're going from 1, which is way up there, to 3, which is way down here. What are we calculating between those 2 points? This is a better word than distance. We're calculating the rate of change from that point to that point. So we would want to calculate the slope. That's all we're doing. When we look at average rate of change, we're calculating a slope. So I'll just make a quick graph here myself, because I suppose I could just put this on the board. That might be easier. Yeah, so this is harkening back to the very first few days we spent talking about calculus. All of derivative calculus is talking about slope. So if we want to find the average rate of change, we're actually referring to the slope from this point to this point. So what would be the easiest way to calculate that slope? Yeah, exactly. I would just do it visually. So it's going down. How many? 4? Yeah, and then going to the right 2. So overall our slope is just down 4, right 2, which is -2/1. And that's the average rate of change. On average, now what does that mean exactly? Like if these are days, and this is dollars, you know, just making up some units on our graph. What does that mean then about the average rate of change? On average, you're losing $2 per day. So every day you're losing on average $2 per day. I'm just making up some units to make it mean something. Yeah. All right, so that's average rate of change. How about number 10? It's been a while since we've talked about limits. How do you calculate these various limits? What does this first one mean? Limit as x approaches -1 with a little negative sign. Yeah, it means approaching -1 from the left. So what is the limit as we approach -1 from the left? Not just 3. -3, yeah. So we're saying x approaches -1. So along the x-axis, we're approaching -1 from the left. And what is our function doing? Along the y-axis, it's approaching 3. Then it can start -3. So the first limit is -3. What about this? What's the limit as x approaches -1 with a plus sign? That means Yeah, from the right. So what happens if we approach -1 from the right? Yeah, then we're approaching -1 on the y-axis. And what about when it just says, what's the limit as x approaches -1? There's only an answer if what? Yeah, if we're actually approaching the same value. So this would be DNE, does not exist. So the limit in general only exists if your fingers are actually approaching the same value. Whereas on the other hand, what if we just want to find the function value at -1? If you plug -1 into the function, what's the output? The actual one, where the actual point is. So f of -1 is actually equal to 1. Okay. Okay, I really am going to skip some problems, but right now I'm liking all of these problems because they're a good review. How do we evaluate a limit like this? We want to know what happens as x approaches 6. Can we just plug 6 into this right now? Because that's all they're asking us to do. They're saying, if I were to look at a graph of this, and I would get really close to 6, what would this function equal? The way to evaluate a limit is to plug the number in. But what happens if I plug 6 into this? Yeah, on the top, -30 plus 30 is 0. And on the bottom, let's see, 36 minus 30 minus 6. 36 minus 30 minus 6. That's also 0. So if I just plug 6 in, I don't know what the answer is. So what do we have to do instead? Yeah, we have to factor. So, yeah, break it down. So how do we factor the top? Yeah, you can pull out a -5, and that leaves behind x minus 6. And what can you do to the bottom?
Factor to 6 -6.
Yeah, we want to know, what do you multiply to get -6? So that's 1 and 6, 2 and 3. Then we'll add to make a -5. And since we're multiplying to make a -6, we're multiplying a negative times a positive. And so it has to be 1 plus 1 minus. So it's got to be the 1 and the 6, and the 6 is a minus, and the 1 is a plus. So that gives us x plus 1, x minus 6. And that's the key that we're looking for. You evaluate limits by factoring the top and bottom and canceling whatever you can. And so now what do we end up with? Now those cancel out, and we just have -5 over x plus 1. Now can we plug in the 6? Yeah. If I plug in 6 now, I just have -5 over 6 plus 1 is 7. And that's what the limit is approaching. I'm going to show this to you graphically so we remember why this is kind of interesting. In calculus, we're looking at expressions that might have asymptotes and they might have holes. So for instance, this particular one, there we go. Oops. Ooh. There we go. So we're approaching 6, right? Go ahead and take a look at the graph. What happens right at 6? Yeah, it's undefined. Why is it undefined? What happens when you plug in 6 in the original expression?
0.
Yeah, you get 0 divided by 0, and that is undefined. But if you just look at what we're approaching, what value are we approaching? It looks like we're getting really close to 0.7. Right? It looks like we're getting close to 0.7 something. And what answer did we get? 5/7. And what is 5/7? Ah, there it is, 0.714. So if I zoom in, I could just, there we go. I could zoom in real good. And if I look now, yeah, see, I'm approaching 0.7146. And that is indeed the fraction that we got. The problem here is that there's technically a hole right there. But even though the hole is right there, our fingers would still be approaching the same number. And so we say the limit is -5/7, even though technically the expression is undefined at that point. Okay, questions about that? All right. In number 12, remember there are 3 rules for continuity. For continuity to exist, there has to be a value at that particular x value. So we're looking, the graph below is a function. What continuity rules are violated at x equals 2? So at x equals 2, First of all, their f of a is defined. That means you actually have to have an output. The limit has to exist, meaning your fingers approach the same number. And finally, the limit exists and is equal to the output. So which one of those rules is violated? Yeah, the very first one. There's no actual point at x equals 2. So there is no output value. Does the limit exist? Do your fingers approach the same value? Yeah, that's fine. But then the third one, does the value that your fingers are approaching, are those equal to the output? Yeah, that's a no, because there is no output value. So technically, rule 1 and 3 are violated, both 1 and 3. Because there's no output value, the limit can't possibly be equal to that output value. Okay. Let's review interval notation real quick. If we want to write the interval notation for when the derivative is positive, when is the derivative positive for this graph? Between when and when? Yeah, is it between -1 and maybe 1 point something? Or we just say 1.5? We'll be friends. So derivative is positive. How do I write that in interval notation? Between -1 and 1.5. Well, just we're talking about when the derivative is positive, so we're just looking at this portion, because that's where the slope is positive. Yeah, from -1 to 1.5. That's the interval notation. Remember, we use parentheses. Why do we use parentheses here? Is the derivative positive at the bottom? What's the derivative at the very bottom? 0. So it's not, the derivative is not positive at the bottom, it's 0. And what about at the tippy top? That the derivative is also 0. So technically, we're not including -1 or 1.5. We're strictly saying between -1 and 1.5. The derivative is positive. Slope is positive. What about when is slope negative? And?
Union with 1 to -1.
Yeah. Yeah, exactly right. Okay, so that's interval notation. All right. Oh, now I should, my goodness, all those problems were on your paper so far, right? Okay, yeah, they were. Okay, 15. Definitely want to do 15 with you. And you can assume that when I say I definitely want to do this one with you, that means it's on the test. More than likely on the test. Yeah, so here we're saying the total cost to produce Q units of good is given by this function. So what do you call the 41,000? What type of cost is that? Since there's no variable next to it. Yeah, that's your fixed cost. And then the 5.8, your variable cost. So what is the total cost to produce 9,400 units? How would we find that? Total cost.
Put in what Q is.
Yeah, you just plug it in, right? So that's C of 9,400. And so you type that into your calculator.
Wait, what number? Is this on the second part?
This is, oh, I guess you don't have that question, huh?
No.
Oh, I'm sorry, okay. So it says, well, that's okay. I still want to review this with you. If you did want to find total cost, you plug it into that function, right? So the total cost, yeah, you're right. You don't have that on your paper. What? Right, you don't have A. But the total cost would be that. That's if you just plug the number into the function. Your question is, what is the cost of the 9,401st item? So just that next item. So you've got a traditional method and a calculus method, and I already told you what they were, right? Like I gave a little definition right there. So the traditional method is to calculate total cost of 9,401 items and subtract the total cost of 9,400 items. Yes, yeah, so you plug them both in. What are you saying, Nado?
No, I'm just asking a question.
Oh, okay, yeah. So that's the traditional method to find the cost of the 9,401st item. And by the way, that's called the marginal cost. That's what this whole question is about, is marginal cost. Margin means the next item, not all the items, just the next one. So we would have to plug that in for both of them. I suppose that's fine that I just calculated that one, because I already have that number. And then if you plug in the number 9401, okay, and then subtract, I got a difference of $5.80. Why does that answer make sense, that that's the cost of the 9,401st item? Yeah, because that's how much it costs per item. And if we consider that our fixed cost was just a fixed cost that we already had to pay, then to produce each additional item, it's really just costing us an extra $5.80 for every additional item. So that 9,401st item was only $5.80. Anyway, that's the traditional method, is subtracting total cost for one minus the total cost of the previous one. So what's the calculus method? Yeah, go ahead and define the derivative of cost is marginal cost. So this word marginal, whenever we use the word marginal, it just means take the derivative. So marginal revenue is the derivative of revenue. Marginal profit is the derivative of profit. So what is the derivative of our function? The derivative of 5.8q plus 41,000? Yep, it would just be 5.8. And then if I plug in 9401 into my input, there's nowhere to put that input. So the answer is still just 5.8. This is a constant function, essentially. So plugging in my variable, or plugging in a value for x, there's no x anywhere, so the answer is just 5.8 for any input at all. Okay, so you'll notice these two approaches gave us the same value right now, and that's because our cost function was so simple. If the cost function was a quadratic or something else, these two numbers might have been different. So which answer is accurate and which answer is an approximation? Yeah, this one is accurate. And this one is just an approximation using the derivative. Yeah, this is exactly how I'll have it on the test. I want to see both. Yeah. All right. Questions about those two different methods, Mario?
So it seems like the only one that's so far good about most of my lessons. Are you going to tell us which ones are good on the test?
I'm not necessarily going to tell you that, no, but I'm going to try to skip around a little bit, yeah, so that we can get through as much as we can. Okay, so number 16 is also a really good one because it covers so many concepts. 16 covers a lot of concepts from this class. So let's definitely look at 16 all together. I'm going to do it over here on this board. So the demand function for a particular item is d of q equals negative 1.25q plus 290, where q is the quantity of items in demand, and d of q is actually what? What does d of q actually represent? What? Yeah, price. So this is that really weird function where we're calling it demand, but really this is representing the price per item. So if you want to sell that many items, that's the price that you should charge to be in line with the economy of supply and demand and being able to sell out of all of your goods without having leftovers and without having people pounding on your door wanting more, but you've sold out. So that's the price to charge. Then what it says, suppose fixed costs of production are 6,000. So now let's come up with a cost function. My cost function, although, you know, I use X a lot, but we could continue to use Q, because Q is just representing quantity. So it says our fixed cost of production are 6,000, and the variable costs are $5 per item. So that's our cost. So before we even read the next couple of questions, What else do we need to define? We already have our cost function. What other two functions do we need? What three functions normally go together when we talk about business situations?
Price, the cost, the number of items.
Well, we do need to know the number of items. What else are we interested in besides cost? We're interested in revenue, and then we're interested in profit. Yeah, so how do we find all three of those? What is our revenue function? Revenue, what's just the concept of revenue? Your revenue is how much money you get for each item that you sell. So a good way to define revenue in English would be what? It's the amount of money you get for every item that you sell times the number of items. Yeah, go ahead, James. Price times quantity, right? Like just think about a really simple business. If you're selling ice cream cones and that's all you're selling, then it's the price per ice cream cone and then the total number of ice cream cones that you sell. So that's always revenue. Revenue is price times quantity. So in this case, what is the price that we're charging?
$5.
No, that was our fixed cost. That's how much it cost us to buy our item. How much are we charging our customers? The what? It's this whole thing. Yeah, that whole thing. Remember, this whole function represents price. This is what we're charging our customers, folks. That's what price means. Cost is cost. That's how much it costs us to manufacture our items. Price is how much we're charging the public. So our revenue, therefore, would be the price, which is that whole thing. I'm just going to write D of Q, times the quantity, which is how many we sell. So we definitely have our cost function already. That's how much it costs us to buy our supplies and make our goods. But in terms of revenue, it's always price times quantity. They gave us a function for price, and Q represents how many we sell. So now let's substitute in that equation right there and actually find out what it is. Our revenue is negative 1.25 Q plus 290 times Q. So we're building our revenue function. And then what can we do? Just distribute the Q and make the formula look nicer. So negative 1.25 Q squared plus 290 Q. All right, so we have a cost function. We have our revenue function. What else do we need? Besides cost and revenue? Profit. And what's the definition of profit? Yeah, revenue minus cost. The definition of profit is revenue minus cost. So in this case, our profit is R of Q minus C of Q. So we want to be very careful when we subtract the cost, because cost will oftentimes have multiple terms in it, and we have to distribute the minus sign. So revenue is negative 1.25 Q squared plus 290 Q minus the cost, which was 6,000 plus 5 Q. So yeah, this is a really good problem to do because you'll have at least a couple problems on the test where you need to build these functions for yourself before you can do any sort of calculus with them. So then what? We have to distribute the minus sign and combine all of our like terms. What do we end up with? So it's plus 290Q minus 5Q. So is that plus 285Q? And then minus 6,000. There. So that was a little bit of a process to just take the word problem they gave us, let the demand function be d of q equals negative 1.25 plus 290. And then the fixed costs are 6,000, the variable costs are $5. And then that's all the information they gave us. And then we had to come up with all of that ourselves. So the conceptual formulas you want to know are the conceptual formula for revenue. So you can build that formula yourself. The conceptual formula for profit, so you can build that formula yourself. Okay, so now what do they actually want us to solve? And the problems that you have on your paper. It says now, what is the regular and marginal revenue from selling the 228th item? Now, I was trying to put two different questions here, and it came out kind of sloppy. What I meant was, what's the total revenue for 228 items versus what's the marginal revenue for the 228th item? So copy what I'm writing down right here. My question for you is, what's the actual revenue for all 228 items versus what's the marginal revenue for the 228th item? Those are the two different questions I was trying to ask. This is just the total revenue, whereas this is the marginal revenue. Just to make sure we all know the difference between them and how to calculate them. So how do we find the regular revenue? Like the total revenue, I should say. What's the total revenue? We just used the revenue formula we came up with, which was negative 1.25 q squared plus 290 q. And you'll just plug 228 into that. Whereas, what formula do we use for marginal revenue? First, we have to calculate the derivative. So what is the derivative of our revenue formula? Now we're going all the way back to derivative rules. So what's the power rule? We're going to multiply by 2 and then subtract 1. So what does that give us? Is it negative 2.5 q? And then the derivative of 290q is just 290. Okay. And at that point, you can plug that all into your calculator. So for the first one, negative 1.25, 228 squared, 290. Okay, that's the total revenue is 1140. Did anyone else get that? Okay. Whereas the marginal revenue, negative 2.5, is negative 280. Now, what does that mean? How do we interpret that result? So far from all 228 items, so far we've brought in over $1,000. But if you actually look specifically at the 228th item and the amount of revenue you brought in from that one, you technically are going into debt at this point for that particular item. How does that make sense? How can we make sense of it? What would be helpful? Let's see, our revenue function was negative 1.2 of x squared plus 290x. There we go. So this is the revenue function. And so you can tell that when you first start selling items, all the way up through 100 items, your revenue is going up, 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 up. So the amount of revenue you're getting is increasing. But by the time you get all the way to what we're looking at, 280 items, your revenue has turned negative. Here. So I guess I'm sharing that with you just to make sense of the numbers and why one of the numbers is positive and one of the other ones is negative. Because in terms of this particular business, your revenue is only positive if you keep your sales less than 232 items. If you sell more than 232 items, you're no longer taking in a revenue. In fact, you're losing money. Okay, well, I suppose we've talked about all of this stuff before. I guess the point is just to review how to do these computations because it's been a while. So now how about the regular marginal cost? What do we do now? I want to do the same thing. I want the actual cost of 228 for all 228 items, that's total, versus just the marginal cost of the 228 item. And then likewise, the regular profit for all 228 items versus the marginal profit for just the 228 items. Everybody go ahead and start working on that. You've got all of your formulas now, and I'll just walk around and help answer any calculator questions or anything like that. Yes. So for this one, oh, okay. Well, then come on up here. I've got it on my.
Yeah, I'm just.
Okay, well, let's compare some answers real quick, folks. Our total cost function was C of Q equals 6,000 plus 5Q. So we'll plug 228 into that, which would be 6,000 plus 5 times 228. So did anyone else get 7140?
Yes.
All right. Whereas the derivative of cost, which is marginal cost, well, that's just 5. The derivative of 6,000 is 0. The derivative of 5Q is 5. And so the marginal cost is always 5. And there's nowhere to plug the 228 into there. The answer is just 5. So the marginal cost for any item is 5. And then we worked out our profit formula, rather lengthy. Our profit formula was negative 1.25 q squared plus 285q minus 600. Is that what you said? Really? 6,000. 6,000, right, folks? I dropped to 0. 6,000. So the actual profit from all 228 items, we would plug 228 into all that. Ooh, and it looks like the profit is negative $6,000 at that point. We kind of already figured that because our revenue was going negative, we're no longer making money by the time we're selling 228 items. Did I do that right? Did anyone else get negative 6,000? You did, Maria? Kristen, you did? Okay. Whereas, what's our marginal profit for the 228th item? Well, we have to take the derivative. So that would be negative 2.5 q plus 285. And so, oops, that's my marginal profit formula. And so if I plug 228 into that, how much profit am I getting from the 228th item? It is also negative. Negative 285. Did anyone else get that? Okay. What would be your recommendation for this company? Yeah, don't sell that many items, right? Go back to before when they were actually making a profit. Okay. Well, I think overall that's a really good problem to review because you had to come up with all the different parts and pieces. We had to come up with our own revenue function, our own cost function, our own profit function, and so on. What questions would you like to ask about that one? Yeah, Anna.
Would you ask for both in each question?
I don't think I'll ask for both in each question. I just made this as a really big, long question to review lots of ideas.
Oh.
I think any one question would be much shorter than that. All right. Well, after that, folks, I think that there are some normal questions where we're reviewing different derivative rules. I don't think we'll do all of these together. Like number 18 is just a basic derivative. You're just using the power rule. Same thing goes with number 19. And number 20 is a little tricky. How about we do 20 together? How do you find the derivative of 3 root x minus 4 over x cubed? Now remember this is derivatives, not integrals. We spent a lot of time doing integrals, so we have to remind ourselves to go back and do a derivative rule. Yeah, you have to change that to be 3x to the 1/2. And then what do we have to change this one? Yeah, move the x cubed up to the top, so it's really, yeah, 4x to the negative third. So first you have to rewrite the function. And now we're doing the power rule. So someone do the first one. Adon, what's the first one, the power rule?
That you add, multiply.
Yeah, you're gonna bring down the 1/2 and multiply it. So 3 times 1/2 is 3/2. And then you
Add 1.
the other. Subtract 1. So when I subtract 1, instead of subtracting 1, I'm going to subtract 2/2, just to make it easier for me to see. So that's the normal power rule. You bring down the number, and then you subtract 1. So that'd be negative 1/2. And then how about the next one? What's the power rule? Wendy? Yeah, so you multiply by the negative 3, so that's positive 12. And then subtract 1, so that's negative 4. Maybe I should have reminded everyone about the power rule. How does the power rule work? F of x equals x to the n. How do you do the power rule? Yeah, bring down the n and multiply, and then yeah, subtract 1. Okay, so we've taken the derivative now. How do we have to clean up our answer? For cleaning up the answer, really, you can just get rid of negative exponents. So how do we get rid of the negative exponents? You just push them back down into the denominator. So this would be, I've got 3 halves, that's 3 over 2, and now I have x to the 1/2 in the denominator. I wrote that in a bad spot. I'm going to bring, so this 3 halves is a fraction, naturally gives me a numerator and a denominator, so I'll put the x to the 1/2 down in the denominator. And then my 12, I'll turn that into a fraction as well, so I have 12 over 1, and I push the x to the 4th down into the denominator. What was the last thing I should do? Instead of x to the 1/2? Yeah. 3 over 2 root x plus 12 over x to the 4th.
Will we use constant to the square root?
Well, I mean, as a final answer, it just looks better. So I would like you to change any x to the 1/2 to the square root. Yeah, that'd be good. Okay, so those few problems were about reviewing derivatives. How about number 23? This is definitely a classic question. You can expect something like this on the test. It says the graph of 2x cubed has 2 horizontal tangents. What does that mean? And keep in mind, during the test, you can use your graphing calculator. What does that mean that this graph has 2 horizontal tangents? There we go, number 23. All right, so what does it mean that the graph has 2 horizontal tangents? Go ahead and make a little sketch of it.
Let's take away the 7.
What did I do? Oh yeah, thank you, jeez. That changes it quite a bit. There we go. Okay, so our graph looks something like that. I should erase. So what are they referring to when they say the graph has 2 horizontal tangents? What part of the graph are they referring to? What parts of the curves? Yeah, the top and the bottom. Tangent is just, you know, where you are tangent to the graph, and they're talking about the horizontal tangent. So horizontal is like this, and so that's one horizontal tangent right there, and that's another horizontal tangent right there. So everyone make a nice graph of that. So for this problem, I would like you to make a graph. Our graph, it goes through the origin. So here's a map of what we're looking at. And it looks something like this. And so we're interested in this point and this point. Those are horizontal tangents where the slope is what? What's the value of the slope right here and right here? 0. So if my slope there is 0, my slope there is 0. So it's nice that we looked at a graph, because graphically, it allows us to know what they mean by a horizontal tangent, but we didn't need to make a graph to solve this problem. What they're asking us to do, they say, okay, this function has 2 horizontal tangents. One occurs at a negative value of x, so that's over here. And then one occurs at a positive value of x, that's over here. and find the location of the horizontal tangent. So they want to know what's that x value and what's that x value. So how do we do it? It's one of our classic techniques in derivatives. What do we do? I want to find where that flat spot is, and I want to find where that flat spot is.
Set the equation to 0.
If we set the equation equal to 0, remember what f of x represents and f prime of x represents and f double prime of x represents? What do those three things represent? This one's the slope. This is the concavity. And what's the first one? Yeah, the y coordinate or the height. So we don't want to set the actual equation equal to 0 because that'll just tell us x-intercepts. So remember here, I'm going to put this up here too. If you set f of x equal to 0, you're finding x-intercepts. If you set f prime of x equal to 0, you're finding flat spots. And if you're set f double prime of x equal to 0, you're finding changes in concavity, flat concavity, where it's not concave up or concave down. So how do we find our flat spots? And we just set the derivative equal to 0. So let's go ahead and take our function, f of x equals 2x cubed plus 9x squared, x plus 6. And we want to take the derivative and then set it equal to 0. Yeah, okay, Mario, you did the first one. So the first one, again, the power rule, you bring down the 3 and multiply, so that's 6x squared. Okay. Yeah, 18x. And then just minus 108. Okay. So that's the slope formula, that's the derivative, and we want to know now, when does that thing equal 0? And yeah, I suppose you could factor out a 6. What I'm going to do first is set it equal to 0. That's what we want to solve. And yeah, do all those divide by 6?
Yeah.
I think they do. So I'll divide everything by 6, just to make the algebra easier. So x squared plus 3x minus, is it 18? And then you can either do the quadratic formula, or you could just factor it. I think it's factorable. What does it factor into? What multiplies to make 18 that adds to make 3?
6 minus 6.
Yeah, 6 and 3. And so now using the zero product rule, this binomial times this binomial equals 0, which means either this binomial equals 0 or that binomial equals 0. So if I say x plus 6 is equal to 0, that means x equals -6, and that's my value over here. Or if x minus 3 is equal to 0, that means that x equals 3, and that's my value up here. Now let's finish this problem completely, because all they said was find the location of the horizontal tangent. To be as specific as possible, we'd like to know that coordinate. So this coordinate is left 6, but how high is it? Where is that actual coordinate? Yeah, what do we plug -6 into? Yeah, the original function. So I'm going to do f of -6 to find out where that is. And then how do I know how far low down that point is? We'll do f of 3. And again, you can do those on your calculator. You don't necessarily have to show a lot of arithmetic on your paper. I got 546 for this one. Oh, you did? And then I got negative 183 for this one. Did anyone else get negative 183? Okay, so what would our final answer to this problem be? The final answer would be a nice coordinate for both of those. This coordinate is located at -6, 546. And this coordinate is located at 3, negative 183. And that would be the true answer to the problem. Find the location of the horizontal tangents. And again, horizontal tangent is just another name for flat spot, or part on the graph where the slope is equal to 0.
This is good.
Okay. We're still in the derivative portion of the review. I'd like to do a couple more of the derivative problems. I had circled a few to do with you guys before we then look at the integrals. So I tell you what, let's take a break because my phone just went off. So we'll take a break and we'll start back up again at 12:03. I tell you what, folks, if you'd like, right now during the break, why don't you flip through the packet and see if there's any problems in particular that you really want to see. Because otherwise, I'll just continue doing the ones that I think are helpful, the ones that I know are going to show up on the test, and we'll just get as far as we can. So let's take a break.
No, but I mean, it's not. It's what? Anyway, it's all the way to
Analyze. Hey, did you get a practice one? No. There you go.
Good. I just probably would walk to check on.
Oh, good.
We just got here.
It was weird. I thought you guys were like a week on there. It was a number.
Well, we want to get the highlight and just sort of things up. He said that we're going to.
All right, folks, let's keep going. So So within the derivative chapter, we have our power rule, but then we also had a couple other rules for doing derivatives. So let's review the product rule and the quotient rule and the chain rule. So number 24, let's do 24 together. As far as the, it says use the product rule, so you already know what it is. How do we do the product rule? What is the verbiage of the product rule? When you have two things being multiplied by each other, how do you take the derivative of them? Derivative of the first times the second plus derivative of the second times the first. So let's do that. We'll do the derivative of the first times the second plus the derivative of the second times the first. So let's start off here. The derivative of the first, I'm going to call on a bunch of you now. So Kristen, what's the derivative of the first part?
2t plus 7.
Yep, so 2t plus 7. So derivative of the first times the second. So I just write down 7t squared plus 6. And then derivative of the second. So let's see here. Karina, what's the derivative of the second one?
14t.
Yeah, 14t times the first one, which is t squared plus 7t plus 7. All right, well, right there is technically the answer. The derivative of the first times the second plus the derivative of the second times the first. So what else would you have to do to this, just to clean it up? It's just a lot of multiplying. You have to FOIL that out and then distribute the 14t and then simplify everything and combine like terms. So I'm going to leave that there. You can always finish up the simplification of it, but that's the product rule. Derivative of the first times the second plus derivative of the second times the first. How about number 25? Here's another good example of the product rule. So we have x squared plus x minus 3 times e to the x. So same thing, derivative of the first times the second plus derivative of the second times the first. So derivative of the first, Daniel?
2x plus 1.
Yep, so 2x plus 1 times the second, so that's e to the x. And then derivative of the second, what's the derivative of e to the x? Of e to the x. It's not 1, it's just e to the x. Yep, derivative of the second times the first. So that's x squared. Now this one, simplifying, is a little different from simplifying this one. Up here, when you just have a bunch of polynomials, you just multiply and combine like terms. How do we simplify this one? Yeah, you pull out e to the x from both of them. You bring e to the x out front, as if you're factoring the e to the x out, and then you're left with the 2x plus 1 plus the x squared plus x minus 3. So you pull e to the x all the way out front, and then you just combine like terms with everything that's inside. So since they're being added, I just go through and I combine all my terms. So there's an x squared, and then I have 2x plus x, that's 3x. Then I have 1 minus 3, that's minus 2. Is that what you all got when you combine like terms? X squared plus 3x minus 2? All right. So that's the product rule. So how about the quotient rule? Number 26, they want to do the quotient rule. So the original function is 2 minus x squared over 2 plus x squared. So how does the quotient rule work? It's very similar to derivative of the first times the second plus derivative of the second times the first. Yeah, low d high minus high d low all over low low or ho ho, either way. So I'm going to set it up with a structure here. Oh, I need it a little bigger. So the structure is O d high, so O d high minus high d ho all over O ho. So see, even writing it out like that might be helpful. So you see the total structure of what we're doing. O d high minus high d ho all over ho ho. So ho, that would be the low one, low. d high, what's the derivative of the top? Yeah, just negative 2 what? Yeah, negative 2x. And then minus high, so 2 minus x squared. D low, what's the derivative of the bottom? Just 2x. All over ho-ho, which is 2 plus x squared. So again, that is the derivative. That's it. That is the derivative, but we can still simplify quite a bit, and you can simplify quite a bit by distributing your 2x and your negative 2x. So let's go and take a look at that would be, you'd have negative 4x minus 2x cubed, and then minus 4x plus 2x cubed. You have to be very careful because this is minus. So you're distributing the 2x in, so the 2x times 2 is 4x, but it's being subtracted, so it's minus 4x. And then 2x times negative x squared is negative 2x cubed, but a minus and negative is positive. And then what happens? What can we cancel?
The negative 2 x cubed.
Yeah, those 2x cubed. So that's negative 8x over 2 plus x squared. Okay, so that's the product rule, the quotient rule. And what's the other rule? The chain rule. So number 27, I'm going to leave that one for you because I think that's kind of basic. Let's do the 28 and 30 for the chain rule.
29.
Hmm?
Really have 29.
Oh, sorry. Yeah, a good point. I should look at what you have. Oh, okay. Let's do 27 and 30. Okay. Let's do 27 and 30. So here's 27. How does the chain rule work? We've got 5, 7x to the 4th plus 5x cubed to the 19th. Notice, because we just spent time doing the integral, you're probably looking at this and thinking, hey, let's do the integral and do u substitution. And you would let u equal that, right? But right now, we're not doing integrals, we're doing derivatives. So we have an inside function and an outside function. So how do we do the chain rule? Nope. Derivative of the outside, leave the inside alone. So derivative of the outside, my 19 comes out, that's what, 95? Leave the inside alone to the 18th. So the basic power rule is that you multiply by the 19 and then subtract 1. And then you leave the inside alone. And then you multiply by the derivative of the inside. So that would be 28x cubed plus 15x squared. And that's it. You just leave your answer that way. So that's the chain rule. Derivative of the outside, leave the inside alone, times the derivative of the inside. Okay, another good one to try would be, oh, I see. What you guys are all looking at the packet that I have in my hands. Okay. So I would like to do R number 30, which I don't have that problem on here. Well, let's do number 30 together, folks. Our number 30 is, are you looking at this problem? F of x equals 6e to the 5x squared plus 3x? Okay, so let's do that one. This is also a chain rule. What's the inside function? Yeah, the 5x squared part. So if we want to take the derivative of the outside, it might help to just kind of cover that up real quick. The outside function is 6e to the. So 6e to the. What's the derivative of e to the? Yeah, the derivative of e to the x is just e to the x. And the 6 just comes along for the ride. So the derivative of the outside function, leaving the inside alone, is still just 6e to the 5x squared plus 3x. That is the derivative of the outside function, leaving the inside alone. Just to convince it to you, what's the derivative of 6e to the x? It's still just 6e to the x. So the outside function, which is 6e to the derivative of that is still 6e to the. So the first part of the chain rule looks the same, because the derivative of the outside is this, but then you multiply by the derivative of the inside, which would be, what, 10x plus 3? And that's that. So a derivative of the outside, leave the inside alone, multiply by the derivative of the inside. Yep, that's how it works. Okay, let's skip ahead to number 44. There we go, number 44. It says, for the given cost function, find the production level that will minimize the average cost. So let's all take a look together. This is the actual cost function. C of x equals 28,900 plus 300x plus x squared. How do you find the average cost? And just think about the word average. How do you normally find an average, like an average of 5 test scores? You add them all up and divide by 5. So here I have a cost for, let's just say, 100 items. If that's the cost for all 100 items, I would then divide by 100. In this case, I don't know how many items I have. It's just x items. So average cost is the cost function divided by x. And that's average cost. So the average cost, you just take your cost function and divide it by x. And so this question is asking us to minimize the average cost. So any problem in calculus that asks you to find a minimum or a maximum, you're going to use the same technique where in order to find a maximum or a minimum, you take the derivative and set it equal to 0. Because you're saying the maximum or the minimum has a slope of 0. And so in order to find that spot, you take the first derivative and set it equal to 0. So how do we take the first derivative of this? At first glance, you might think you need to use the quotient rule. But fortunately, we don't have to do the quotient rule. What can we do instead? Can we split it up into 3 different fractions? Sure. That'll make life a little easier on us because then that's 3 different derivatives that we can do. So, but then each one is simply the power rule. There. So it cleans up quite a bit. Would it still work if you did the quotient rule? It would still work if you did the quotient rule. You can feel free to do the quotient rule. But this is definitely faster and less computations to do. So you can always split up a fraction over a single denominator by taking each part of the numerator and putting it over that denominator. And then you can simplify. So what's the derivative of 28,900x to the negative 1? Ashley, what's the derivative? Yep, very good. And then subtract 1 from there. And what's the derivative of 300? Just nothing, 0. And the derivative of x is just 1. So now we have this function, That's our derivative. I'm going to go ahead and call that average prime of x. That's the derivative of our average function. And what do we want to do with this? Ideally, we want to set it equal to 0. Not just 0, though. A flat spot, anytime you find a critical point, you're looking for when the derivative is 0 or undefined. So let's take a look at this function real quick. Our derivative of average, the average cost that is negative 28,900 over x squared plus 1. And we can either set that equal to 0. That's one thing we could do, is set the derivative equal to 0. Or we could say, when is this thing undefined? So when would this fraction be undefined? Yeah, when x is 0. So x equals 0 is technically another critical point. But does that make any sense that we'd want to know the cost of 0 items? Yeah, that's not really what we're looking for here. They're asking us to find the production level that will minimize the average cost. I mean, certainly producing nothing, that could minimize the average cost, but that's not really what we're interested in. Okay, so we need to solve this. How do we do it? We want to solve for x, which is currently in the denominator. Well, we do need to get it out of the denominator, but not just by pushing it as a negative exponent. We genuinely want to solve for x. Yeah, well, first let's move the 1 over, or better yet, I'm going to move this term over. So that'll give me 1 equals 28,900 over x squared. And then what? How do you get x squared out of the denominator? Yeah, multiply both sides by x squared. And that way, we just have x squared equals 28,900. And when you square root both sides, you get x equals plus or minus 170?
Yes.
Right, and then does the negative part make sense? I mean, yeah, so that you can't have a production of negative 170 items, so we're really just looking at 170 items. 170 items will minimize the average cost. Now, what could you do on test day? Can you use your calculator and graph all that? Sure you could. You could just use your calculator and type in that whole function, and then find the min or the max. So just to show us what that looks like, there's our function. And here's the graph. And you can tell that the graph does have a bottom point. Oh, there it is. And what do you know? It's at 170. I can make my graph look better. There we go. So yeah, you can see that there really is a bottom to that graph, and the minimum is at 170, which is what we just calculated. Okay, now that's not the end of the question. It said the production level that will minimize the average cost and the actual minimum average cost. So how do we actually find what the minimum average cost was? What do we do with that 170? We plug it back into the actual average cost function. So we would want to now take our 170 and plug it into there and find out the actual minimum average cost. So, of course, my graph just showed it to us, but on your calculator, you have to type it all in, 28,900 plus 300 times 170 plus 170 squared, and then all divided by 170. Did anyone else get 640? So the actual average cost was 640 based on 170 units. There. All right. Well, that to me was all of the derivative questions that I most wanted to do with you. That doesn't mean that the other questions aren't on the final, but I thought those were some really good ones to review. What questions would you like to ask about the derivative questions? Folks, I have a question for you. Would it be helpful? By the way, have I ever told you about the teacher cave? You guys are college students, so you might not, you know, we don't think about teacher caves now, but in high school, I always told my students that there was a teacher cave. And it's where all teachers went at the end of the day. Because, you know, teachers don't really have lives. They just go to a teacher cave and hang out with all the other teachers until the next day when they can go back to school and be in their classroom. Have you ever heard about this, the teacher cave? It's just a joke. Anyway, because after I leave today, I'll go to my teacher cave. I was wondering, would any of you find it valuable if I filled out this whole thing and posted it? Would that be helpful to you? Would you really look at it? Would you really study from it? Because, I mean, it would take me time in my teacher cave to do that, but I would do it for you because we're not going to be able to get through all of this. But so long as you find it useful, then I'll go through and I'll fill this out. Did I tell you the other day I filled one of these out by watching Labyrinth? Did I tell you I watched Labyrinth the other day? Do you remember the movie Labyrinth with David Bowie? Oh man, it was great. Okay, so I'll go home to the teacher cave and I'll watch a good movie like Labyrinth and I'll fill this out and I'll post it hopefully later tonight. Okay? All right. Well then, that's it for the derivative portion. Let's talk about integrals. And was someone raising their hand? Yeah, Wendy.
Are we turning this in on Tuesday?
I don't think I'm collecting it for a grade. Yeah, I don't think it's for a grade. I mean, that's an interesting idea. I appreciate that you'd want extra credit. I mean, my first idea for extra credit for everyone in the room is to finish Math AS because that's a significant portion of grade opportunity. Let me see here. So wait, you're really asking if you can get extra credit for having filled out the entire practice test? Yes, I'll give you extra credit. If you turn in the entire practice test, I would give it to you. Yeah, no, this is not for a grade. Do you guys want it to be for extra credit? Okie doke. Of course, it kind of cheapens it then that I'm going to post all the solutions. Because, I mean, then you could just theoretically go in and copy them all down. But, hey, even that, I suppose, is going to be good practice. All right. Well, let's keep going. So, integral questions. We did just finish the integral unit, so I don't think we necessarily have to do all of these. Which ones would you like most to see? Like, yeah, from the integral section now. So flip to the next page where it says integrals. Why don't you guys go ahead and flip through right now and choose some that you'd like to see. And I'll still kind of keep in mind what I think you need to see. So far I heard number 20. Any other big ones popping out at you that you want to see? 26. Yeah. I'll definitely do one like, oh yeah, 20, 21. Okay, well let's start at the beginning here. So, what did you say? Yeah, sure. Yeah. In fact, that's a fine place to start. All right, there we go. There's number 5. It says evaluate the definite integrals. So the first one, Kristen, go ahead and read it to us. What area do they want? Yeah. So just take a look right there and draw a shape around it and calculate that area. So how many total squares are there in there, Kristen? Well, just between 0 and 1 and underneath the curve. There is 1 square, another square, and half a square. Yeah, 2.5. That would be it. I realize they're not squares, they're rectangles. But they're square units on the graph in any case. So the area from 0 to 1 is 2.5. Does that make sense, everybody? And Kristen, how about the next one, from 1 to 9? Okay, so that area was 2.5. From 1 to 9 is a little more tricky because we have to remember the difference between area above and area below. What's the area below? It's negative. So I would start by finding the area over here. So how many squares are there, Kristen? Yeah. You've got a half a square, and then 1 square, so that's 2 over there. So that's a total of positive 2. Now how about over here? How many squares do we have? Well, how much is this thing? That's a whole square, isn't it? Yeah. So that's 1, 2, 3, 4, 5. So that's negative 5 over here. So then if you add positive 2 and negative 5 together, you get a total of negative 3. All right, and that's just in keeping with the idea that area above the axis is positive and area below the axis is negative.
From 1 to 9.
Oh yeah, from 1 to 9. Okay. Folks, let's skip ahead here. I want to comment on number 9 and 10. So number 9, this is really just a definitional rule. It's not very exciting. Yeah, number 9, if your function is an integral, and when you take a derivative of an integral, what happens? When you take a derivative of an integral, yeah, the derivative and the integral cancel out, and you essentially just substitute that variable into the function. And so the answer is just x to the 8th. It's not very exciting. It's a definition. And in any case, that now is the derivative of the original function. So if your original function is an integral where the upper limit is a variable, and you take the derivative of it, the integral cancels out, your x becomes your new variable, and that's the derivative. And so what would f prime of 3 be? Yeah, 3 to the 8th? I don't know what that is. 6,000 something? Sorry, what is it?
6,561.
551?
61.
The 61. 561. All right. Wait, did I finally get it?
Yeah.
All right, thanks. Okay, so that was number 9. What about number 10? Now they want the second derivative. So in number 10, you've got the function is an integral going from 0 to x of t cubed plus 6t squared plus 3. And so the first derivative does what? The first derivative just cancels the integral and puts an x in for all those variables. So you have x cubed plus 6x squared plus 3. And the second derivative does what? Actually just takes the derivative of that, which is 3x squared plus 12x. Yep. So that wasn't very exciting. The next few problems are all just integrals. I feel like we've done a lot of integrals as of lately. So, yep. If you just want to see a couple, the integral of 7 over x, I would bring the 7 outside, and it's the integral of 1 over x dx, which is natural log. So that's just the 7 times the natural log of x. Yep, that's number 11. A couple of these were on your recent test, so I could review one of the ones that was on your test lately, like for instance, number 14. How would you take the integral of x cubed minus 4 over x plus 2 over x cubed plus 6 root x? Yeah, you do each one individually. You might want to prep these two first. So the integral of x cubed, that's still 4 over x, but then this would be 2x to the negative 3, and that would be 6x to the 1/2. And then, yeah, you just take the integral of each one individually. So the integral of x cubed would be what? So remember now, we're doing the antiderivative. So you're going to start by adding 1 and then dividing by the result. What about the integral of over x? Yeah, that's just the natural log, so that's minus 4 natural log of x. And then this is another antiderivative, so or anti-power rule, so you would add 1, so that's to the negative 2, and then divide by the result. And again, this last one, you'd add 1 first, so I'm going to add 2 halves. So that'd be x to the 3 halves, and then divide by the result. So 6 divided by 3/2. We do that right? So cleaning that up a little bit, that'd be 1/4 x to the 4th minus 4 natural log x minus 1 over x squared. And then 6 divided by 3/2 is the same as 6 times 2/3, which is 12/3, which is 4. So that'd be 4x to the 3/2. I'm about to give you your test back, so definitely review a problem like that because it might show back up on the final. I tell you what, number 20 won't be on the test. So you can just cross out number 20. Number 20, you can cross it out. But we should do at least one U substitution. Which U substitution would you guys like to do, 19 or 21? Maybe 21? Let's do 21 as a U substitution. Oh yeah, there we go. So we want to do the integral of x to the 4th times the square root of 12 plus x to the 5th. And again, we want to do U substitution. So what will we let our U be? Yeah, the 12 plus x to the 5th. We know that's a good choice because when we take the derivative, we get 5x to the 4th, and there is an x to the 4th out here, so we know that is helpful when we bring the 5 over. So 1/5 du equals x to the 4th dx. So now what? What do we replace? We can do the square root of u, and then the dx and the x to the 4th get replaced by du and the 1/5. Now how do we solve that integral? We still have a few steps to do. Yeah, let's move the 1/5 out, and then what do we do with that square root symbol? Yeah, make it u to the 1/2. And now we can just do the normal antiderivative for the power rule, the anti-power rule. So we add 1, so I'm going to add 2 halves, so that's u to the 3/2 divided by 3/2. I still have my 1/5 out front. And now we just have to clean all that up. So fraction-wise, dividing by 3/2 is the same as multiplying by 2/3, and that's u to the 3/2. So that's 2/15 u to the 3/2. Did we do that right? And so now we just back substitute with our u, and we're done. 2/15 12 plus x to the 5th to the 3/2. Okay, well folks, I know that we didn't get to do every single problem from the practice final, but you can go back through your old homework assignments as well as your previous tests and find solutions like that. When you go home tonight and over the weekend, if you have any questions, you can just email me and I can help you via email. And keep in mind that you can also look up solutions on mat213. If you go into mat213, you can watch those videos to review solutions there as well. Hey, where did Luis go? And where did Adam go? He had to work. Yeah, he's going to have to work. And where did Adam go? No? Okay. All right. Well, folks, go ahead and take some time right now since we still have a couple minutes. take some time right now and look at your tests and see if you have any questions that you want to come ask me.